Everyone. Today I will be presenting on image super resolution using deep learning. This topic focuses on reconstructing high resolution images from low resolution input images, which is very useful and helpful in many real world applications. So, coming to the introduction, what is actually a low resolution image, or what is the input we are going to give, and why is the or what is the need of a high resolution image? So at first, what is low resolution image? The images which is having limited number of pixels or data points, which is having poor clarity, blurry or blocky details. It will be having small file size, but information loss will be there, and they are hard to analyze, find features or structures. And like, what is the example for a low resolution image is that if you take a group photo using a basic camera mobile phone from far away, you cannot see everyone's face clearly. So that is because there are not enough pixels to present that particular details. Now, why do we need a high resolution image? So high resolution means more pixels. That means more data points, which allows us to capture tiny details very clearly. It will be having better clarity and sharpness. They are useful for tasks needing precision, like medical imaging, satellite imaging, and all. And it allows us zooming or cropping without losing the quality. These are the needs why we require a high resolution image. So what is meant by image super resolution? So coming to that, image super resolution technique, or what is meant by image super resolution, is that it is a technique to increase the resolution of an image. So yeah, so how to improve the resolution and image? What is meant by image super resolution? It converts a low resolution image into a high resolution one. So now you understood what is low resolution image and what is a high resolution image and what is the need for that. So that is known as a image super resolution. So it helps to restore lost details like edges, textures, and fine patterns. And it is often needed when original HR images are unavailable or costly to obtain. And super resolution is a process of enhancing the resolution of an image. A LR image might be, or low resolution image might be blurry or lack details. So using the super resolution, we recover those fine details. Okay. Now, why is SR important? The same thing we discussed. What is the need for high resolution image that I'm discussing again? It's applications of, or we can call it as the applications of this super resolution images. The first one is medical imaging. So, in order to enhance the MRI or CT scans for better diagnosis, the second comes the satellite and remote sensing for improving the details in aerial or spatial images. And third thing is security and forensics, like for face clarity, like for the CCTVs and surveillance footage. Next is entertainment for upscales the videos or photos for 8K or 4K display. And so it goes on. So in sectors like surveillance and healthcare, for better clarity can directly improve the outcomes. So next come, what are the different types of super resolution? The first one is single image super resolution. Single image means one image, one low resolution image we are converting into high resolution image. That is enhancing the resolution using only one low resolution image. For example, sharpening a blurry face photo into a clearer one. Got it. Next is multi-image super resolution that combines information from multiple low resolution images of the same scene to reconstruct a sharper HR image or high resolution image. For example, using a several satellite images of the same area to generate a clear map of what we are going to present or what has been captured. The last one is video super resolution. It improves the resolution across video frames while keeping motion smooth. So these are the different types. Last one is video super resolution. It improves the resolution across the video frames while keeping motion. That example is we'll be converting the old 480 pixel movies to HD or 4K without losing the details. And SASR is most common and mostly used in deep learning super resolution. So, okay, coming to the traditional approaches, what were the basic approaches we were using? The interpolation methods are the one we were using as a base methods to blur, zoom, or rotate, or for any kind of interpolations, we'll be using any of these three. First one is the nearest neighbor, which will be considering the nearest pixel, and in bilinear, we'll be considering the nearest 4 pixels, and in bicubic, we'll be considering the nearest 8 pixels. So those are the simple mathematical techniques that estimate new pixel values based on nearby pixels. Okay, they are fast and easy to implement, but they have so many drawbacks also. It produces a blurry or smooth end result, especially at higher scaling factors. It may lose so many edges, details, and textures, and it might be giving some jagged or blocky edges. So, and it cannot come up with some new details or cannot create some new details or missed details. So that is one, that those are the drawbacks. So they, in one of an image which has, this is a Lena image, which is a very famous image in image processing, and the nearest neighbor bilinear and bicubic methods have been applied, and it shows the result. Bicubic will be having a more smoother image, while nearest neighbor will be having a blocky kind of image. So the complexity of the algorithm is more for the bicubic, and this gives a comparison of a low resolution as well as a high resolution image. And next comes a deep learning. So why deep learning? Why we are using deep learning for this super resolution techniques? So learns mappings from low resolution to high resolution directly from the data instead of relying on handcrafted rules. So here, what deep learning is used, why we are using it, it captures a complex pattern, textures, and semantic information. Example: facial features, natural sceneries, etc. It is able to utilize very deep architectures like CNN scans, transformers to model non-linear relationships. So it learns high frequency details from the data set, like CNN, GANs, and even transformer models are there nowadays to produce visually realistic output. So DL does not just stretch pixels, it predicts the missing details. And there are uh, these are the popular deep learning super resolution models. The first one is SRCNN, which is the first learning deep learning approach. Second is FSR-CNN, which is a faster version, that is faster super resolution CNN. Next is VDSR, that is a very deep super resolution network. Next is next is a GAN based SR GAN, that is generates realistic textures. And the next one is ESR GAN, which improves over SR GAN using RRDP block, or it is an enhanced SR GAN. And the last one is a transformer based, that is SWIN IR. So, what is meant by SRCNN? SRCNN means a super resolution CNN, which is the first deep learning based super resolution method. It has simple three layers that CNN is mapping from low resolution to high resolution. It improves PSNR compared to interpolation. This PSNR is a matrix which is trying to evaluate a resolution of an image. Okay, so it is simple CNN improvement over interpolation methods. So the limitation is it is slow and cannot upscale large images effectively. The next one is the faster resolution. So on top of this SR-CNN, we build this fast super resolution CNN. So it is lightweight and faster improvement over the SR-CNN. It applies most computation in row resolution space. It uses deconvolution for upscaling, and it is faster and lighter version, and it is good for real-time usage. It is real-time for performance on devices like mobiles. And the next is VDSR. So next one is VDSR, that is very deep super resolution. In here it is very deep because it is having 20 plus convolution layers like a VGG network, and it uses a residual learning model, focuses on low details, and it handles multiple scale factors like by 2, by 3, and by 4. And it is having better edge recovery than the previously discussed SRCNN as well as FSRCNN, which is, so since it is deeper, it is having a better edge recovery and better capturing of the lows details. So that is about VDSR. And then comes the SR GAN. So what are meant by GANs? What are meant by GANs? GAN based super resolution. We will be discussing next. One is SR GAN and next one is ER GAN. So SR GAN means super resolution GAN. So what are GAN based super resolution? So there are many GAN based one, SR GAN, ESR GAN and all. GAN means generative adversarial network. So two neural networks fights like rivals to improve the image quality. There will be one generator as well as one discriminator. This generator tries to create a high resolution image while the discriminators judges whether the results look real or fake. So there will be one generator and discriminator. Both will try to make this generator learns to fool the discriminator, improving a realism each round. Okay, so why GANs are awesome for super resolution? It introduces a realistic texture in SR, and I told that there is one criteria like PSNR. Here in GANs, the PSNR will be very less, but it will be having some but improving the row this thing visually pleasing, though it have lower PSNR than the other classical methods. It will be having more visually pleasing features, or visually it will be more way more pleasing than the other ones. So this one, SR GAN introduces the GANs for SR. It is more realistic features. It uses a perceptual loss instead of only PSNR. So it uses one more metrics to evaluate, that is perpetual loss, that I'll discuss in the next coming slides. So it doesn't it don't- not only uses PSNR. Next, it is great for phase, natural scenes, movies, etc. So the next one is ESR GAN. It has enhanced SR GAN. It is a state of the art GAN based SR model. Now it uses residual in residual, that is RRD blocks. There are certain blocks. So the difference from SR GAN is that this uses this particular blocks in order to enhance the performance. Next is replaces the batch normalization. It will be sharper you might have learned deep learning what is batch normalization and all. So by applying that, replacing with batch normalization, it makes it more sharper details and fewer artifacts. It is the best choice for movies, animations, and satellite images. And the last one is a transformer based this thing image restoration, that is swing transformer for image restoration. It is based on transformers or attention based learning. It is the most advanced one which is currently existing. It models long range dependencies and global context. As I discussed, it has a strong performance for what and all things, for image SR. Then, yeah, as it uses a transformer attention for global context, and it is a state of the art performance which can show images for visual improvement. And yeah, next comes the SR CAN. It is why it is telling about SR CAN. It has some visual improvement. So apart from this SR CNN and fast SR CNN, this SR CAN improved, brought a visual improvement in the images by adding adversarial loss for textual accuracy and produces the sharper edges and realistic details. So then there are something called training loss functions. So what I meant by this, next we will be discussing about training loss functions. So the basic or main loss functions which we are using to evaluate or calculate the losses in or finding out errors or in image resolution is super resolution is L1, L2 loss, perceptual loss, and adversarial loss. So what is meant by L1, L2 loss is that it is a pixel level correctness or pixel accuracy. It minimizes the difference between the generated and ground truth image pixel by pixel. It produces a smooth and clean results but may lose texture details. So it is very every pixel is close to the real one or not, then the accuracy is like that. Then perceptual laws means it is based on the visual similarity as perceived by the human eyes. So it uses deep features like from VGG networks and all instead of raw pixels. It preserves the textures, edges, shapes better than L1 and L2. So it makes we'll be thinking like does the output look realistic to a human eye? That means it checks the visual quality. And the last one is adversarial laws or GAN laws, which by the name itself we can understand this will be applied for the GAN models. So it focuses realism and natural appearance, makes the generated image look like real world image by fooling a discriminator. Very effective for fine textures but may introduce artifacts if unstable. So what basically it is doing is that can it pass as real to another network? That is checking the realism boost whether it is realistic or not. So actually L1 L2 ensures the numbers match, perceptual makes ensures like human like what they see, and adversarial ensures model believe it's real. Okay, next is performance evaluation. What are the performance or metrics used for evaluation? The first one is the PSNR or peak signal to noise ratio. It measures the pixel wise reconstruction quality and sensitive to noise and distortions. So higher PSNR means more accurate results or more accurate pixels. Then second one is the SSIM, that is structural similarity index, that compares the structure, contrast, and luminance, represents how close the shape and patterns are to the original one. And higher SSIM means better structural similarity. The next one is LPIPS, that is learned perceptual image patch similarity. That means deep feature based perceptual similarity aligns more with the human visual judgment. Lower LPPIS means more visually pleasing output. Okay, and which is having higher values means it will be giving better qualities despite others GAN and all. If it is having very less PSNR also, its other features will be have to be more realistic. And here is a visual comparison of low resolution bicubic and ESR GAN output are given. And for the bicubic, it will be more blocky kind of. All the other CN, SRF, SRCNN, and ES, RCNN, every others will be giving more better results compared to the low resolution and bicubic. So here is again one more resolution. You can see the last. So in IR is having a better clarity and resolution, high resolution, which patches all the details and making a more real or clear image. So what are the current challenges with these high resolution models? The first thing is the limited training data for some domain, and next is the hallucination of the fake details, like imagining some fake details and adding it. Next is computational cost will be very high because and the transformer models need more GPU power. So the final ones are the future research directions. So it is a real-time SR deployment can be done, and secondly lightweight and mobile friendly models, and the video aware temporal consistency, and finally a multimodal SR. So these are the future research direction which can be done in further. So we have discussed about a basic idea about what is image resolution, low resolution image, and what is the need for high resolution image. We discussed about the applications, what are the different types, and what are the latest available ones. And it's